Chris Kurzik from AES. Welcome back. A little bit about our company, what we do. We provide equipment re-rating and fitness for service services, and reliability and safety studies, short-term staffing that we've been providing, and training and certification, materials and welding studies and investigations, and estimating and economic evaluations. And we've been getting into environmental studies like carbon footprint and emission studies. So let's dive into what we're going to work on today. To the fourth and final part of our study of fatigue basics so that we can look further into detail for ASME. So we looked at welds, weld metals, and parent materials as well, because I'm looking and sort of comparing how they're closely related. And so this is sort of an overview of what we've been going through in the previous videos. We looked at the different stages of cracking, the propagation, non-propagation, which I find really interesting. And the studies, the studying that we've done is just basically sort of a summary, because there's a lot of work that's been done on this, and I don't really feel like we've done work enough justice, but it does provide hopefully enough basis so we can understand ASME a little bit more. And so we looked at the topics, and so the last one we're going to look at is welding procedures, how we can make that welding procedures more, the end product more fatigue resistant. We're going to look at some of the welding processes and consumables and gases, and what they can do for us, and the benefits of post-weld heat treatment, which is always very interesting. And even when we do other ASME ones, like 579, the section on cracking, there's some really interesting discussions about post-weld heat treatment, and some really interesting calculations that I found in the last year that were really interesting. And then we're looking at fatigue, welding designs. There's a couple designs out there. ASME will get more into that, into those specific type of designs that they like to ensure service, so that fatigue doesn't become an issue, or in cases. So let's continue with part 4, our final part. Material characteristics. So what we found was the performance of a component under fatigue loading is influenced by the physical properties. So the melting point of material, the thermal diffusivity, the thermal expansion coefficient of the base or filler metal. So as our temperatures go up, then we would expect that the fatigue life could be affected by that. Mechanical properties include tension and the hardness and the ductility. The corrosion resistance, which we talked about earlier. And the metallurgical properties like the microstructure. So parameters related to welding. So we've got welding parameters, should include, in the welding procedure, the weld bead geometry, okay? And, so we're looking at, tempered beads, so using very small beads is a strategy to reduce the, residual stress in a part. We look at the weld joint configuration. Fillet welds form nucleation sites more easily than butt and groove welds. Fillet welds are not considered to be, proper welds for, fatigue surface. You want to try to get to a butt weld or some kind of groove weld. And the residual stresses in the weldment, compressive stresses in the residual stresses are desirable. So that means if you peen the welds, that you create compression in the weld, and that's a desirable thing. And the properties of the weld in the heat affected zone are something that has to be included in the welding parameters. So let's look at this some more detail. So these parameters affect the fatigue life by, weld continuities, stress risers. We've got, weld thermal cycling, residual stresses developed due to experienced by the weld, by the metal being welded. So these will, affect things the welding stresses, right? And then we have the mechanical properties such as the strength, the hardness, and the ductility of the parent material. And we continue with this. So then we look at our weld procedure. We have the welding procedure requires the following. So edge preparation is very important. So we want a mechanical or thermal methods for preparation. We want a mechanical or chemical cleaning is important for the preparation. And we have, a selection of the welding process. So, whether we use a low or a high density process is important. And parameters, so welding current, welding speed, and welding consumables. We look at the electrode diameter, the filler, the flux, the coating, and shielding gas, and the post-weld heat treatment. And also one last thing is shot peening, or stress relief. So that's looking at putting it in the oven and to reduce the stress in the welds, which is when I looked at the API 579 in more detail, there's sections on that where you can actually do a calculation. You can see the effects of stress relief, and perhaps I'll do that in a future video, and it's really quite remarkable. One calculation I did basically demonstrated that the stress could be dropped by like 90% by doing stress relief, and like in terms of reducing the internal stresses in the part, which is one of the key elements for reducing improving the fatigue life of a part. So a little bit more on edge preparation. So edge preparation influences the fatigue performance of a weld. So cleaning is really important. In mechanical one, is preferred. So that's like cold grinding, right, and getting the reducing the residual stresses off the surface, and that's the preferred method. There's another method which is a chemical cleaning, and the problem with it is that these chemicals have hydrogen, and these hydrogen-based metals can create a hydrogen diffusion, and it can potentially create a cracking issue, because you got to remember the part is getting really hot when you weld it later after cleaning, and the surface can have that some hydrogen which can go inside the steel, and that would be more of a case with like a carbon steel or an alloy steel, where that's a big situation. But again, I think the industry standard, at least in Canada, is mechanical. And for cutting, cutting of metals to be welded by fusion or weld process, really thermal cutting increases the hardness of the surfaces. So if you have situations where you have a high hardenability material like a chrome moly, then you want to be grinding those materials. So let's look at the process. Welding process affecting the fatigue performance. So we've got this net heat input per unit area is related with the welding process, and the cooling affects the welding structure. Okay, so we also want soundness and cleanliness of the weld. is an issue. The next thing is the welding process generates heat by developing an arc which is supplied to the base metal for melting of the mating surfaces. Welding process. Heat generation from electric arc, which is voltage times current. Welding process depends upon the weld voltage, which is V, right? And then the welding current I, the amperage. And the heat supplied is affected by the welding speed, okay? And the welding speed. And therefore, the heat supplied is obtained by a ratio of the arc heat generated and the welding speed. So when they do the qualification of the welding, they have to be able to balance this to make sure to optimize the heat input into the weld. The next thing is high cooling rates, right? If you have rates that are too high for cooling, or high for cooling, then you're going to get a finer grain structure with good mechanical properties and toughness, and that's desirable for improved fatigue performance. So consumables, let's talk about consumables. So depending on the weld process that is being used for fabrication of a fusion weld, a variety of consumables is considered. So the welding electrode, so the diameter for the heat input, the filler wire, the shielding gas, the flexor coating composition, and the basicity index. Now, the electrode composition, the composition of the electrode material affects the solidification mechanism of the weld metal, and it affects the residual stresses in the weldment, and that's a function of the thermal expansion coefficient of the weld metal relative to the parent material, and the mechanical properties of the weld metal is important when we look at the electrode composition. So improving the fatigue joint performance. So improving the weld load carry capability by enhancing the mechanical properties. So that would include, electrode or filler metal achieve a fine coaxial grain structure. So this is what we want to achieve. So equally axial. So that means that the shape is very round. We don't want sharp edges on the grains. Weld procedure, we want we want to control the weld procedure to maximize the mechanical properties of the microstructure. And residual stress risers, we want to reduce those. And in order to develop, we want to develop favorable compression stresses. So that means strategies can be, shot peening or changing the configuration of the weld or the part so that they're not an issue. So shielding gas. Let's talk about shielding gas. Shielding gases, in industry they include helium, argon, carbon dioxide. I've just used quite a bit of that to foundry, and mixes of gases with oxygen and hydrogen. So argon is what we see a lot of in Alberta, especially for fatigue type welding. But let's look at these gases. So the gases can affect the fatigue performance, and how do they do that? Well, welding gases protect the welding pool from contamination. So they prevent inclusions and porosity. So that's why helium and argon are recommended. Again, I don't have much experience with the helium, but the argon more familiar with. And you know, that's one of the reasons why they're doing that. And another thought here is the heat generation. So, you know, I always knew it for protecting contamination, but this is something I learned later, that it actually assists in the heat generation to assist in the weld penetration. For example, helium results in high heat generation and improved weld penetration compared to argon. So if you have a situation, you know, a strategy would be to you know, change your welding gases to assist in that. Carbon dioxide can also improve heat generation. So, you know, in the steel foundry where I worked many years ago, they tended to go with that strategy. I think back at that time, the gases were cheaper as well, and so they were more concerned with, you know, making sure that there was enough penetration to ensure that the part would join, because they were working with, you know, materials that were you know, high on the hardness side, and they wanted to make sure that there was no going to be, you know, proper fusion, so there'd be no crack development. So relieving the residual stress also, you know, reduces potential distortion in the part. Like if you look, for example, for, you know, like structural components, like for a pump base, for example, there's a lot of welds in there, and so you want to reduce the potential distortion in a part, you know, when it's loaded, and you know, after it's been fabricated, that you know, you don't want the part to, you know, distort, because it would affect the performance of the rotating equipment. And then you have to look at the post-weld heat treatment also modifies the microstructure. Okay, and it also, again, it relieves the residual stresses, but it also modifies the microstructure. So when we have that, because we, you know, sometimes we can't control the cooling, right? So then we get a lot of martensite in the structure. So we have to, so by post-weld heat treating it, and in ASME, there's all kinds of rules for that, for vessels and equipment and cooling rates. And the casting, the Metal Founders Society has standards for that as well. But anyway, so you want to take the martensite, which is a very hard microstructural material, and you do the post-weld heat treating, and then you get the softer structures, and which includes bainite and pearlite, which are good, you know, tough materials, and they're desirable in a microstructure. And you know, and another thought here is mechanical properties. So normalizing, quenching, you know, that cycle of normalizing and then followed by a quenching cycle improves the toughness by making sure that the grains are more uniform and small and round, right? And that's achieved by, you know, by normalizing to get the grain size correct, and then followed by quenching. So, you know, and so at the end of the day, if you follow, you know, the post-weld heat treatment, you can get a homogenization of the structure, the weld to the parent metal in the HAZ zone, and you could get better properties with this homogenization, because there's less chance of you know, defects from forming. So stress risers. Examples of stress risers could be ripples in the weld surface, could be cracks in the weld, and in the HAZ, the heat effects zone, the sharp change in the cross section at the toe of the weld. And there's some really interesting shapes that we can talk about in another video, if there's a request for that or a clarification. You know, you have too high of a head angle, you know, in the head, or we have excessive reinforcement in the weld bead. It can sometimes be an issue. We can get crater or underfill. I'm going to continue this, you know, poor bead geometry. This is interesting. So we can get, you know, a proper selection of the welding parameters can keep weld bead angles low by keeping the current and the speed low. So that's something to consider. So manipulating the arc, welding arc, and the placement of the molten metal. Sometimes with, say, tempered bead welding, where you use very small welds, they plan the where they place the beads to ensure, you know, the grains are small. And so and by doing that, you can promote remelting of the welds and, you know, and dressing of the weld. Here's some interesting configuration that I used before. This is sort of a strategy that's used sometimes in things where there's a lot of fatigue, like a coke drum, where there's a lot of cycling going on, and so a trick that's used where, you know, we're worrying a great deal about, we have an area where there's just a ton of fatigue, you know, thermal cycling, you know, pressurizing, you know, several times a day. This is a very common strategy. So instead of having, you know, the weld in the high stress area, you move it off there and you put large radiuses on your bends, and in making sure your vertical loads are directly over your, say, this, if this is, say, for example, your skirt, then the vertical loads will translate to the skirt. So that's one very common strategy that's recommended by ASME. Now here's another weld configuration. So if you look at the one on the left, we've got an area of high stress locations. So if we do practice a strategy of, you know, grinding, and we can, you know, smoothen out those transitions, and then it will certainly help in reducing, you know, the stress concentrations on the weld. So developing compressive stresses. So we can reduce the tensile stresses by inducing compressive stresses, you know, and this is where we talked about shot peening. There's a strategy called overloading, something that I've never really tried, like spot heating, and, you know, post-weld heat treating as well can help. These ones are a little bit more trickier. Shot peening is, you know, or hammer peening the weld is something that I've seen more common. But, you know, if someone has some thoughts, I'd love to hear that. I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.